Last year in grade 11, I for the first time took physics. One of the most interesting concepts I learned in that class was simple harmonic motion. Simple harmonic motion refers to the simplified model of motion of objects that move in some sort of constant, periodic, and predictable way, for example, a pendulum or a spring. It's a basic version of the movement we observe in the real world, which is more closely modeled by a more complicated system known as dampened harmonic motion. In this video, I'll focus on talking about horizontal springs on a frictionless surface, because you're probably familiar with springs and their behavior, and this setup allows me to explain the concept without getting too many complicated equations in the way. Now we all know a spring has a certain resting length, or equilibrium point, and if we just assume it's a perfect spring, immune to friction and wear and tear, we can also say that when it is stretched or compressed, it'll try to restore itself to its equilibrium. In 1675, Robert Hooke, a scientist studying springs and elasticity, discovered that the extension of a spring is proportional to the force, and thus Hooke's law came into existence, describing the force of a spring. The equation he used is F equals kx. So what do those letters mean? Well, the F obviously stands for force, as measured in newtons. The x is the displacement of the spring in either direction from the spring's equilibrium. The distance from that point to the equilibrium is known as the amplitude, and it's equal on both sides. It's also usually measured in meters, as it is the SI system's standard. Now the all-important K is the spring constant, or how stiff or springy the spring is. It's how much energy or force it takes to actually stretch or compress the spring. It's proportional to the cross-sectional area of the spring and inversely proportional to its length, and it's measured in newtons per meter. Now you might notice that after you compress or stretch a spring or move a pendulum past its equilibrium point, letting it go won't make it go back to its equilibrium. In fact, it'll overshoot the equilibrium, and then it'll go back and overshoot it again. This is because of energy. In a closed system, like in simple harmonic motion, you put in energy to compress or stretch a spring. However, without removing it in waste energy as friction or heat, the energy remains in the system and continues to switch between potential and kinetic energy. We can actually better understand this by seeing the potential energy and kinetic energy over time as a spring is stretched and compressed. Now if you take the motion of the spring, or a pendulum, over time, and graph it, it would make a sinusoidal wave, which is the same graph that's used to describe things that have circular motion. Because mathematically, simple harmonic motion and circular motion are very closely related. While the concept only gets more complicated from here, I hope I've explained using visuals a concept which I initially thought was difficult to understand in a more approachable way. Thanks for watching.